spend much time working out examples. Because I figured, I already mentioned that you should take a look at the end of chapter problems. And if you have any questions about end of chapter problems, we can cover those.
Yeah, are you going to post an exam like you did last time?
Yeah, we'll post the exam.
Do you know when you're going to post that?
I can post it today. So this is what I assume people are doing, if you have time, of course. You do the, of course, these aren't worth any points, but these are valuable because these will show you the breadth of the types of questions that are answered. So assuming that some people go through, especially if you have time, like how many, 7-1 number of atoms, how many atoms of each element are in the formula unit of ammonium phosphate? Well, ammonium phosphate, we got to write out the formula for. What is the formula for ammonium phosphate? Just brought my pen. What's the formula for ammonium phosphate? NH4. That's right. So NH4 for 3PO4. So how many nitrogen atoms do we have? 3 nitrogens. How many hydrogens? 12 hydrogens. 1 phosphorus. 4 oxygen. Something like that. So there are problems with that. You want to know that. 4. It may be said that because atomic, molecular, and formula masses are all based on carbon-12, they are conceptually alike. Well, what then are their differences? Atomic, molecular, and formula masses are all based. What is atomic mass? Well, atomic mass is how much an atom weighs. So this can be U per atom. So atomic mass. Atomic mass of carbon-12, for example, C12. Molecular mass would be like CH4, U per molecule. So carbon-12 weighs exactly 12 U. CH4 is carbon's 1201, hydrogen's 101, 1605 U. These are useful to memorize, so you can do these calculations in your head. I mentioned before. So that would be like a molecular mass. And then what was the other one they're asking? The formula mass. Formula mass and molecular mass are the same thing I mentioned. Formula mass is the general term used for any formula. Molecular mass is used just for molecules. And so some things don't form molecules. And so formula mass we have to use for sodium chloride because sodium chloride doesn't form molecules. So sodium I don't have memorized, so I just looked that up on the periodic table. It's 2299. So sodium is 2299, and then chlorine is, I have chlorine memorized, 3545. And so we get, 5844. And so one unit, that is one sodium and one chlorine, is going to be 5844 U per formula unit. And so how are they alike? The masses for they're alike because they're the masses. If we have one carbon atom, that's a mass. If we have one methane molecule, that's a mass. If we have one sodium and one chlorine ion, that's a mass. What are the difference? I don't know what their difference is. The difference, obviously, one is used for atoms, the other is used for molecules, and this is the formula is used for everything, including. So I'm not really sure what they're asking. 6. In what units are atomic, molecular, and formula mass expressed? U per atom, U per molecule, U per formula unit. I'm doing the blacks. You should do the blues. This is what I mentioned before. I wasn't planning to do chapter 7, but unless you find this useful, we'll do it. Is it useful? All right, we'll do this then. Determine the formula or molecular mass of each substance. You know, when you go through the entire thing, then you know the entire breadth of problems that are going to be asked. You know, and obviously there's some problems that can be outside the scope of this, challenge problems, but you're going to be much better prepared for a challenge problem if you have all these problems down. And so this is what a lot of students end up doing. Determine the formula or molecular mass of each substance in the following list. Nitrogen trifluoride, is that molecular or is that what we call a ionic compound? Is that molecular or ionic compound? I think it's a molecular compound. Nitrogen trifluoride. So nitrogen trifluoride, what's the formula? NF3. So we have one nitrogen, 1401, 3 fluorines. 3 fluorines, fluorine I don't have to memorize, we just looked that up. Fluorine is 18.99, is that right? Yeah, 998, so we have to round that, unfortunately. So we're going to get a little bit of round off here, so I'm going to go with 1900. So 3 times 1960 minus 3 is 57, so it's going to be 5700. So this would be 7101. 7101 would be this. So 7101. But we might as well jump ahead because we know something. We know the definition of the mole. So this is going to be U per molecule. And I might as well jump ahead because this is an advantage of doing this later. It's also 71.01 grams per mole of molecules. Mole of molecules. This one, since I don't want to do a whole bunch of repetition, this one's called the molecular mass. What is this one called? The molar mass. Yeah. Molecular mass, molar mass. Now, molar mass is like formula mass. It's just used for everything, whether it's molecules or ionic lattice. It doesn't matter. We use molar mass for everything. Molecular mass is just specific just for molecules. Barium chloride, I mean, this is the same thing. You know, this is useful because it's just additional nomenclature practice. But barium chloride, BaCl2, right? So we look up barium. What is barium? And then 2 chlorines. So barium is 137.33. 137.33. Chlorine is 2 times 35.45. So we have 2 chlorine is 70.90. So this is 3, 12, 8, 11. Now what? 20. 218, 23. That would be, now barium chloride is different because is barium chloride molecular or ionic? It's ionic. And so what we'd say here is we'd say 218.23, right? 218.23 U per formula unit. A formula unit would be 1 barium ion and 2 chloride ions, not molecules. So formula unit, or 218.23 grams per mole of formula unit. So if I had a mole of barium and 2 moles of chloride ions, then that's how much it weighed. Lead-2-phosphate. What's the formula for lead-2-phosphate? I'm sorry, erase that last part. 218.23 grams per mole of formula unit. Lead-2-phosphate formula? Okay, correct. And so here we have 3 leads. How many phosphorus? 2 phosphorus. How many oxygens? 8 oxygens. So we just sum it out. So what you do, when you do this kind of stuff, of course nomenclature, the more practice you get with nomenclature, the better. But, as far as the masses go, this is pretty straightforward, would you say? If you find it straightforward, then you just skip ahead. If you don't find it straightforward, then you keep working at it. It's like Newton. And so this is why I thought Newton was a brilliant idea because, I remember taking math and just going, oh my God, this is the same problem over and over and over again, and I'd be doing the same problem over and over and over, and all of them were required, so I had to do it. But I found it so repetitive. It would be nice that, the ones that you find very repetitive, you don't have to do so many. And so you do fewer of those, and the ones that you find challenging, you do more of those, so you can work on the areas that you need. That way you don't waste so much time. And so you hit a point where, oh man, this is so easy, you just skip ahead, right? And so adding these masses up is pretty easy, would you say? Or if not, then do more. If yes, then skip ahead. Writing these formulas out, easy. If not, then do more. If yes, then skip ahead, Because you're going to obviously you're going to have nomenclature, that you're going to have to do, so. Let's move on. So I like this because we could tailor it to our needs, and the answers are there. Calculate the mass of each of the following molecules. Nitrogen dioxide. Nitrogen dioxide is 1 nitrogen, 2 oxygen. Nitrogen is 1401, 2 oxygen is 32. So it's going to be nitrogen dioxide is 14 plus 32, 46, 4601. 4601 U per single molecule. If I had an Avogadro's worth of these 6.022 times 10 to the 23rd molecules, it would be 4201 grams. Dichlorine monoxide. Dichlorine, 2 chlorines and an oxygen. Dichlorine, this is molecular also. And so chlorine, 2 chlorines is 70.90, oxygen is 16. So it's 95.90 U per molecule, or 95.90 grams per mole of molecules. Explain what the term mole means. What does a mole mean? This is like explaining what a dozen means. Well, a dozen means 12, right? And so you could say a mole means 6.022 times 10 to the 23rd, but you should go beyond that, because where does that number come from? Where does 6.022 times 10 to the 23rd come from, originate? That's the number of atoms in exactly 12 grams of carbon-12. That's the way the number. And so the mole comes from that. It's the number of atoms in exactly 12 grams of carbon-12. That's defined as 1 mole. Why do they pick such a weird definition? The reason they pick such a weird definition is so this works. If they didn't pick that definition, this would not work. Let's say that instead of picking 6.022 times 10 to the 23rd molecules or formula units, let's say they picked an easy number. Let's pick 1 times 10 to the 20th. 1 times 10 to the 20th is a lot easier to remember, right? 1 times 10 to the 20th, would it weigh, if I had 1 times 10 to the 20th formula units or molecules, would it weigh this many grams? No, it weighed a different number of grams. Well, what is that number? Well, we'd have to figure out that number. And just because of the way we define the mole, these two are numerically the same, which makes our life a heck of a lot easier. A heck of a lot easier having that Avogadro's number. And so why is it used in chemistry? It's so important because it gives us the dual relationship between molecular, atomic, and formula mass with molar mass. We can easily relate the two because numerically they're the same. 14, give the name and value of the number associated with the mole. Avogadro's number, 6.022 times 10 to the 23rd. Is it an exact number? Is Avogadro's number exact? Are there exactly 6.022 times 10 to the 23rd carbon-12 atoms in exactly 12 grams of carbon. 12, no, it's not exactly. It's 4 sig figs, that's correct, and that's what you're going to memorize it through. 16, how many molecules of boron trifluoride are present in 1.25 moles of this compound? The boron trifluoride is a molecular compound, BF3. So 1 mole is 6.022 times 10 to the 23rd plus a quarter mole. A quarter. In other words, we do stoichiometry. This is the beginning of stoichiometry here. You could just do this dimensional analysis thing. Do this dimensional analysis thing. 1.25 moles of BF3. And then we know that there's 6.022 times 10 to the 23rd, whatever, units per mole. And so, what are the units here? Well, these are molecular units. So what we could say is that there's 6.022 times 10 to the 23rd molecules per mole molecule. If it's formula units, I would say formula units, but it's ionic.
Wouldn't you, at the bottom, wouldn't you use moles of barium trifluoride because it has to cancel?
Yeah. And so that's correct. I do moles of BF3 molecules. And that cancels. Sometimes, most of the time, people leave off this molecule here. Does it say moles of BF3? But this is moles of BF3. What are the units of molecules? This is not to be confused with molecular mass. It's just, you know, I have a dozen eggs, right? And so there are two ways you could write it. You could write it 12 eggs per dozen, or you could write it 12 eggs per dozen eggs. Because dozen eggs doesn't mean the same thing. So that's all I'm doing. But I'm using molecules, you know, so I'd have 12 molecules per dozen molecules. How many moles of boron trifluoride are present in 7.04 times 10 to the 22nd molecules of this compound? Sorry. How many moles of boron trifluoride are present in 7.04 times 10 to the 22? So if I have 7.04 times 10 to the 22 molecules, then I'll just use Avogadro's number again, 6.022 times 10 to the 23rd molecules per mole. Or molecules, but I just leave out the molecule because you start getting so this tells us how many moles. Then we figure out how many C6 we're allowed for this. Let's see that calculator here. So let's do the first one. 1.25 times 6.022. 7.527 times 10 to the 23rd molecules. Around 7.53 10 to the 23rd. So 7.04 times 10 to the 22nd divided by 6.022 times 10 to the 23rd. 0.1169 moles. I'm allowed for you to say big 0.117 moles molecules. See how many moles of nitrogen dioxide are present in 7.89 times 10 to the 22nd molecules of this. It's going to be close. Well, the number we just calculated. So 7.89 22nd. Nitrogen dioxide, NO2 molecules. .022 times 10 to the 23rd NO2 molecule, mole, molecule. Let's just say for mole of NO2. 7.89 times 10 to the 22nd divided by 6.022 times 10 to the 23rd. 0.131 moles. Let's round it. 0.131 moles. How many molecules of nitrogen dioxide are present in 1.60 moles of this compound? So if we have 1.60 moles of NO2, then there's 6.022 times 10 to the 23rd NO2 molecules per mole. And so 1.6 times 6.022 times 10 to the 23rd gives us 9.635. 10 to the 23rd molecule of NO2. Rounding this, so it's going to be 9.64 times 10 to the 23rd NO2 molecules. All right, 18.8. How many atoms of hydrogen are present in 2.69 moles of water? So we have 2.69 moles of water. Now, I told you that the formulas are atom or mole ratios. So if I have H2O, I can do this as 2 atoms to 1 atom. Or I could do this as 2 dozen to 1 dozen. Or I could do this as 2 moles to 1 mole, okay, of oxygen. This is hydrogen, this is oxygen. And so the easiest is just to do it like this. I have 2 moles of hydrogen atoms for every 1 mole of H2O molecules. And so for every H2O molecule, I have 2 H atoms. For every mole of H2O molecules, I'm going to have 2 moles of H atoms. And so this is what we call a formula relationship. Formulas are atom or mole ratios. Atom or mole. This mole ratio, atom ratio is the exact same thing because a mole is just like a dozen, you know. And so it's the same. It's a number. And so in other words, for every 12.044 times 10 to the 23rd H atoms, I'm going to have 6.022 times 10 to the 23rd H2O molecules. Okay, now we'll figure out how many atoms are present. There's 6.022 times 10 to the 23rd H atoms for every mole of H atoms. So everything cancels out except the number of H atoms. So this is next level. So 2.69 times 2 times 6.022 times 10 to the 23rd. 30.239 times 10 to the 24 basic figures. How many moles of oxygen are present in 1.39? These are all dimensional analysis. This is why I said dimensional analysis is one of the most important problem-solving techniques. All these problems are dimensional analysis. If you're good at dimensional analysis, you'll be good at all these. So we have 1.39 times 10 to the 22nd H2O molecules. And then we want to go to moles of oxygen. So from H2O molecules, we can easily go to moles of H2O. Because there's 6.022 times 10 to the 23rd molecules per mole. Molecules. So I'll just write this as just an arbitrary or undefined unit here. 1 mole of units is 6.022 times 10 to the 23rd of those units. And so this takes us to moles of H2O molecules. From moles of H2O molecules, then we know that for every 1 mole of H2O molecules, how many moles of oxygen do I have? 1 mole of oxygen atoms. And so that takes us to where we want to go here. So this is going to be 1.39 times 10 to the 22nd divided by 6.022 times 10 to the 23rd equals 0.02308 moles, or 0.0231 moles, or 2.31 times 10 to the minus 2 moles of oxygen atoms. Oxygen atoms, O atoms. All right, 7-4. Continue. How does molar mass differ from molecular mass? Well, molar mass is the weight of a mole of molecules, 6.022 times 10 to the 23rd. It's going to put it in the gram range. Molecular mass is the weight of a single molecule, which is in the U range. And so the units are different. Molar mass is grams per mole. Molecular mass is U per molecule. Numerically, they're the same. Numerically, they're the same because of how the mole and the U are defined. It's actually brilliant, the whole thing. And really, you got to sit there and sort it out mentally to see how that works, because it is incredibly useful. Calculate the molar mass of each of the following: chromium-2 iodide. Because of the duality, there's a duality here between atomic mass and molar mass, and molecular mass and molar mass, and formula mass and molar mass. Chromium-2 iodide, what's the formula for chromium-2 iodide? CRI2, good. So we have 1 chromium, 2 iodines. And so 1 chromium, oftentimes we don't write the units for this. Chromium is 51.996, so we're going to just have to go with 5200. We don't write the units here because they're double units. 5200 U per atom, or 5200 grams per mole of atoms. And then 2 iodines. Iodine is what? Okay, 126.90. We'll leave it at that. And so it'd be 2 times 126.90. So 127 would be 254. 253.8. 253.80. Again, this could be U per atom or grams per mole. Now, is this ionic or molecular? It's ionic, so we can't use molecular mass. We would call this formula mass. The formula mass would be, this 52 plus this is going to be 305.8. So 305.80 U per formula unit. The molar mass would be 305.80 grams per mole of formula units. So what are they asking for here? They're asking for the molar mass, so this would be it. Silicon dioxide. I'm going to speed up the pace. Silicon dioxide, what's the formula for that? SiO2. And so silicon, they want the molar mass, so I don't care about the atomic mass. So if I want the molar mass of silicon, it's 28.07. 08. We have to round it, unfortunately. 27.09 because it's 8.5. Gotta round up. 2 oxygens is 32.00. And so this is going to be 59.09 grams per mole. Carbon tetrafluoride. What's the formula for carbon tetrafluoride? CF4. CF4. Carbon is 1201. Fluorine is 1900 times 4. So 19 is 20 times 4 is 80 minus 4 is 76. So it's going to be 88.01 grams per mole. This is grams per mole of molecules. And so this is grams per mole of molecules. And so we have molecular mass. Molecular mass would be, what about SiO2? Does SiO2 form molecules? Yes or no? You would think SiO2 forms molecules, but it doesn't, because you should know SiO2 is known as silicon dioxide is known as. You don't have this in your notes anywhere? Maybe you said it 4 times. This is another thing. If you have the luxury of time, everybody could be, everybody could ace this class if they have time. It's just a matter of reviewing and kind of memorizing the stuff. That's it. The problem is everybody forgets 90% of the stuff, and then they struggle with the test. If you remembered everything, then there's no problem. You'd be fine. So SiO2 is known as quartz. Does quartz form molecules? No. Quartz forms a lattice structure. And so unlike CO2 does form molecules forward. So we would say formula units here. This would be formula units. This would be formula units, molecules. Carbon tetrafluoride, yeah. Okay, let's move on. Section 7-5. Conversion among mass, number of moles, and number of units. Find the number of moles for each mass of substance given. 53.8 grams of beryllium. 53.8 grams of beryllium. What's the symbol for beryllium? B is actually boron.
No, Be.
Oh, Be. Okay. All right, B. All right, let's hear it. And so, actually on the periodic table we got the molar mass right there. Beryllium is 9.012. 9.012. This one I'm going to carry 3 decimal places. The reason I'm going to carry 3 decimal places is because I want 4 sig figs. Normally we only carry 2 decimal places, but there are some exceptions. The exceptions would be single digits. We have single digit here, we want three decimal places. You get 4 figs. So grams of beryllium cancel, that gives us moles of beryllium. So 53.8 divided by 9.012. 53.8 divided by 9.012, that gives me 5.969. 5.969. I'm allowed 3. I'll carry 4 here. Moles. Moles. Beryllium. Which is going to be 5.97 moles. Okay, the next one is C3H4Cl4. Would you call that tricarbon tetrahydrogen tetrachloride? Would that be the correct name? True or false? False. That naming system is only used for what? That naming system is only used for binary molecular compounds. This is a molecular compound, but this is not binary. And so we don't use that naming system. The name of this if you go to organic chemistry, you'll learn the name of this. Organic chemistry, there's a whole bunch of new nomenclature rules you have to memorize. And that's it. A lot of people struggle in organic chemistry because it's a lot of new rules that you have to memorize. And so some people say, actually there's an interesting debate. Some people say, organic chemistry is one of the hardest classes out there. Some people don't. Some people would argue against that. But the people that say that it's one of the hardest classes out there is because of the amount of stuff you have to memorize. A lot of stuff. It's not that bad. I didn't find organic chemistry that bad because it worked out a system for memorizing stuff. It worked out okay for me. C3H4Cl4, so I don't care about the name of that. We aren't going to worry about the name. But organic chemistry deals mostly with carbon and hydrogen, then some other elements. Chlorine's one of the big ones, so I have that one memorized. So carbons, if you've got 3 carbons, it's 3 times 1201, which is going to be 3603. And then we have 4 hydrogens, which is 4 times 101, which is going to be 404. And then we have 4 chlorines, 70, 90, 140, 1.8. And so it's 4 times 35.45. This is going to be 141.8. Thank you. Yeah. 9 and 9, 1.8. Is that it? Yeah, that's right. And so that's 3, 7, 7, 8, 180, 187. 180, 187. And then this is this molecular? Yeah. So grams per mole, molecular. And so we have 781 grams of these molecules, C3H4Cl4. And for every mole of molecules, it weighs 181.87 grams. And that gives you moles of molecules. And so what does that come out to? That comes out to the 781 divided by 181.87. 4.294. 4.294 moles, which is 4.29 moles. Calcium hydroxide is next. What's the formula for calcium hydroxide? I'm sorry, what is it again?
So Ca.
Ca.
And then OH is going to be the parentheses too.
OH parentheses. Good. That's correct. So calcium is, what is it, calcium? 40.08. Rounded, it's going to be 40.08. Two oxygens, you probably can do it in your head. Two oxygens, 3200. Two hydrogens is 202. 74.10. 74.10 grams per mole. Or U per, what is this, molecular or ionic? It's ionic. So we wouldn't call it molecules, we call it formula units, or formula mass would be U per formula unit of this. So we've got 0.756 grams of calcium hydroxide. Now we know the molar mass, 74.10 grams per mole. This is one of the most common conversions, is a gram to mole conversion. If I want to be a little bit more thorough in my labeling, this would be it. So this gram to mole conversion, but we don't usually stop here. Stopping at moles is premature because we usually go all the way. It's hard to measure moles. The way we measure moles is indirectly through measuring mass. If there was a balance that measures mole, that would be fantastic, but there isn't. And so we always measure mass, or we measure volume, or we measure something else and then convert it. And so this is 0.756 divided by 74.1. 0.01020 moles of calcium hydroxide formula units. So 1.02 times 10 to the minus 2 moles of calcium hydroxide. If it's like this, I usually don't use scientific notation. If it's like this, I would write it 0.0102 because that takes up a lot less space than this. So I would have left it like this in decimal form rather than scientific notation. Uh-huh.
You have to write like moles per formula unit?
We have to what?
Do you have to write moles per formula unit? Or
No, just moles.
Okay.
But you know,
No.
but the thing is, the problem is this. People do the shortcut without learning the long way. You know, the proper way of doing it is to do it correctly and then take the shortcut. But if you just go straight to the shortcut, then you don't know. Are you talking about formula units? Are you talking about molecules? What are you talking about, right? And so eventually, a lot of people do the shortcut. They don't write it because they assume you already know it. The problem is you start asking people and they don't know it, you know, and so that's it. And so I'm going to eventually quit writing a lot of this stuff and then just do it the shortcut way. What do you think of these? Are these pretty straightforward, or like a little too, you know? Although the nomenclature is good, maybe we'll do that. Cobalt-3 bromide. What's the formula for that? Yeah, COBr3, good. Ammonium dichromate. I don't like this. The book gives you dichromate. Unfortunately, you have to memorize dichromate. And so the homework is not going to be like the test. The test is going to be harder because I'm not going to give you dichromate. I expect you to know dichromate. And so ammonium dichromate is going to be the formula for ammonium dichromate? Yeah. NH4-2Cr2O7. This is a dangerous compound. Why? It's a dangerous compound. Ammonium salts are soluble, it dissolves in water. It's dangerous because ammonium salts dissolve in water and you'll get chromium-6 in water. Chromium-6 causes cancer. So it's dangerous in that way. Is that the only danger in this? Is the health hazard of chromium-6? No, there's another danger to this. You should know the chart well enough to know what is one chemical property of dichromate that stands out. Chemical property of dichromate that stands out. It's a strong. Maybe you haven't. The thing is, you want to have some time to once in a while look at this chart. The more times you look at this, the more it's not like you have it in your memory at all times. It's in your subconscious, maybe. You know, hey, wait a minute, I've seen that. I've seen dichromate before. Where did you see dichromate before? It's a strong oxidizer. So you kind of register, yeah, dichromate's a strong. What are the strong oxidizers? You should know some of these. Fluorine, permanganate, chlorine, dichromate. Powerful. Dichromate's a powerful oxidizer. What about ammonium? Ammonium is not on the chart, but ammonium is it's a acid, weak acid. And so you might have registered it. It's a weak acid. Ammonia is the base. Ammonium's the acid. It's weak, somewhat insignificant acid. But when paired with a powerful oxidizer, I worry about something about ammonium. What do you worry about in terms of ammonium? Is ammonium electron rich or electron poor? It didn't click. All right. That's what. Well, let me just let me say one more thing. The best time to review stuff is immediately after class, because that way, one thing, because I being a student, I was very curious about memory. My memory's bad, and so I started reading some stuff about memory as a student. The best time to remember is immediately after the information's been presented. And how rapidly you lose that is shocking. How fast, you think about how many hours are wasted by relearning stuff that if only you could remember. And so there's one guy who was saying that you could save, you could save hours and hours and upon hours of wasted time if you just review. And he had a specific, he worked this out. He said the first time you review the material is like the day after or the day of. And then something like every other day for the first week. And then once a month or something like that. He had it worked out. This guy was a memory champion, by the way, so I was watching his video. So I thought, oh yeah, that's interesting. That makes sense. Did I tell you about my friend who wanted to go to medical school? I didn't tell you about him. He's when I was at UCLA, I had a friend who wanted to go to medical school. He knew I was a chem major, so he asked me for help with chemistry because the MCAT has a large percentage of chemistry. And so he was graduating, and I was graduating, and he was about to take the MCAT, and so I said, sure, I'll help you, And I thought he remembered a little bit of chemistry. He didn't remember any chemistry. He had the chemistry, it was like 3 years since he had chemistry. He forgot everything. And so when we sat down and started to go through the chemistry again, it was like starting from scratch. And so it was impossible. There was no way he was going to be ready for the MCAT. And so he had to delay it because what he had to do was go back and relearn everything because everything was white clean. I mean, white clean. Think about, 4 years ago, what do you remember? Do you remember what happened on a particular day 4 years? No, I don't, unless you have some kind of special memory. I have no idea. And so anyway, how long did it take him to review? It took him, altogether, it took him 4 years to review the material. So after he graduated, he got a part-time job and then spent the next 4 years reviewing everything and learning it on his own, basically. He did take a very expensive course. I forgot the name of it. And he did fail. I think he took it multiple times, but he did fail to get into medical school in the U.S. So eventually he gave up in getting into medical school in the U.S. and then he went. He applied to a Caribbean medical school and got in. But it was very expensive, the Caribbean medical schools. But they had a little easier standards for getting in. But anyway, maybe it's okay. Maybe you can forget all this stuff. But anyway, we talked about ammonium. What was it, yesterday, didn't we? Or the day before yesterday or something? I don't remember. But it was recently. What was ammonia? What was the charge on nitrogen? The charge on hydrogen is +1. Do you have this in your notes? What's the charge on nitrogen? -3. Is that electron rich? Maybe, maybe not, but yes it is. Yes it is, because I'm telling you, this is electron rich. This stuff burns. You can burn ammonium salts easily. You don't want to burn them because you'll form toxic gases, but you can burn ammonia, you can burn ammonium salts because they're electron rich. Not the hydrogen. Hydrogen is okay. And so this is dangerous because you have a powerful oxidizer and a good reducer in the same compound. We've seen that before. We saw that before in 2 compounds. Can you name them? What are the 2 compounds we saw this before? One was Pepcon. Maybe it was last week. That's it. It was last week. Did I show you the Pepcon explosion in Nevada? No? Okay, maybe my memory's really bad. All right, this is one of them. This is called ammonium perchlorate. This is an ammonium perchlorate plant in Nevada near Las Vegas. 2 people were killed in this explosion.
Hits. You're about to see some of these.
Okay, I don't want this one. I want this other footage. Was this it? Not this one. This one. So ammonium perchlorate is dangerous because it has the fuel and the oxidizer in the same compound, like this. This is different than something like the sodium perchlorate or potassium perchlorate. If we're looking at sodium perchlorate, then we don't have to worry about this because sodium ions are already oxidized. And perchlorate is an oxidizer. And so this is just an oxidizer. This is a lot safer because there's no fuel. This is a lot more dangerous. Ammonium perchlorate is a lot more dangerous because the fuel and the oxidizer are in the same compound. Did I show Texas City? You remember Texas City? All right, Texas City, that was a huge disaster, 600 people.
Exposed to intense heat.
But have you seen this? Did you see the China explosion? That was Tianjin, China. Okay, you have to watch out. This is the language on this. It's about.
Holy shit! What kind of video is that? What the fuck?
Might be a gas station or something.
What kind of gas? Whoa! Oh! What the? No fucking way! No, baby! No!
Are we dangerous here?
Yeah, we're dangerous! Oh my god! Oh dear!
Are you filming?
Yes, I'm filming!
Wow! I think we are there.
I know.
Let's go!
Why are you still there? Bro, do it That was insane.
Yeah, that's well. Yeah, Texas City had way more fatalities. I think it was only 140 people dead. Only? Yeah, I shouldn't say that. So yeah, it's pretty bad. You would expect a lot more fatalities or something like that. What was that? You know what that was? That was ammonium nitrate. That one. We talked about this, didn't we? Ammonium nitrate versus sodium nitrate. Chemical properties. Didn't I ask you about the chemical properties of ammonium nitrate? Yeah, that was on the quiz. So anyway, the best time to review is afterwards, so you remember. So it's something close. Otherwise, it's easy to forget. Me, I forget. That's why I ask people to write things down for me so I don't forget. But my memory's getting worse. But you know, I remember this stuff, this chemistry stuff, because I see it over and over. That's it. It's just repetition. You know, you don't have to be any kind of genius or anything. You just have to go over it repeatedly. That's the thing that most people don't do. Most people don't do that, and then all of a sudden, if you do that, then you get like. Once I figured that out, then I was getting top grades in the class. You know, one of the top grade in the class. So do that. It's not that hard. I remember the film class. I took a history of French film. You know, and I think I got one of the top grades in the class. It was so easy. You know why it was so easy? Because she let us record the lectures. And so I'd record her lectures, and then when I went to sleep, I just put on the headphones and just listen, and then she fell asleep. You know, it was a good way to go to sleep. But then when the test came, it was just the same stuff, exact same stuff as she was talking about. And so it's just repetition. That's how you can learn chemistry and do well in chemistry. Well, anyway, let's take a look at ammonium dichromate's dangerous stuff. 8.80, so this one's a little bit more difficult to figure out the molar mass, but we could do it quickly. Here, how many nitrogens? 2 nitrogens is 2802. How many hydrogens? 8 hydrogens is 808. 2 chromiums? Well, chromium, I'm not going to look that up. We looked that up earlier. 51.99, so it's 52.00, so 104.00. 7 oxygens. 7 times 16. 7 times 16. 6 times 16 is 96. So add another 16 would be 112. So it's 15, 16, 20, 22, 4, 5, 252, 15. And so what do we have here? We have 8.80 grams of ammonium chromate, dichromate. 8.80 grams of ammonium dichromate. And then a mole of this weighs 252.15 grams. We figure out how many moles we got. 8.8 divided by 252.15. 0.03489 moles. 0.0349 moles. Okay, normally what I do is I double check my calculations, but I don't have time to double check my calculations right now, so this is why. But I would normally do that as just part of standard procedure. Magnesium perchlorate is nowhere near as dangerous as ammonium perchlorate. And so if that plant was manufacturing magnesium perchlorate, they would never have blown the plant, Pepcon, that is. If Pepcon was manufacturing magnesium perchlorate, they'd still be around. Why? Oh, magnesium perchlorate still be different. What is the formula for magnesium perchlorate? Yeah, this would have been stable as long as they didn't mix it. This is oxide. In redox, we have the oxidizer and we have the reducer. The reducers we call fuels. So metals are fuels, ethanol's a fuel, sugars are fuel. Anything with extra electrons are considered fuels. Methane's a fuel. Methane's very electron rich. It's fuel. And so this one is missing the fuel because is magnesium ion a good fuel? Magnesium metal, if I mix magnesium metal, then I'm in trouble. If Pepcon was manufacturing both magnesium and magnesium perchlorate, then the explosion would have been even more horrific because magnesium is an excellent reducer, excellent fuel. Okay, 28.3 grams. So it's the same thing. We have how many magnesiums? 1 magnesium, 2 chlorines, 8 oxygens. And then we figure out, just add them up. So let's skip this. So, because this is we're going to see more of these types of calculations also. Calculate the mass of each substance from the moles given. So this is just molar mass stuff again. What's the formula for sodium hydrogen carbonate? Well, I'm looking at 28A. Sodium hydrogen carbonate has the formula Na HCl 3. Good. Silver nitrate, what's the formula for silver nitrate? silver nitrate. Sodium hydrogen phosphate. Now, the problem is that monohydrogen or dihydrogen? Since they didn't say specify, I'm going to assume that must be monohydrogen phosphate. And so what's the formula for sodium monohydrogen phosphate? Na3HPO4 is incorrect. Yeah, sodium monohydrogen phosphate. Yeah. Na2HPO4 is correct. That's because H is +1, sodium is +1. So this is 3 plus altogether. Phosphate is 3 minus. Yeah. It's because of the hydrogen ion we're adding to it. So this is sodium hydrogen, calcium bromate. Formula for calcium bromate. CaBr2 is incorrect. CaBr2 is called calcium bromide. Calcium bromide. Bromate. BRO3. Is that it? That's wrong. Yeah, that's right. So anyway, there's plenty of stuff to do. If you don't have these ions memorized, then memorize them any way you can. You know, whether it's flashcards or whatever, however you memorize things, just memorize it that way, whatever you're comfortable with. If you don't have a specific method, then just try different methods. I tried a whole bunch of methods for memorizing these things until I found something that worked for me. But just because it worked for me doesn't necessarily mean it works for everybody. So, you know, you got to play around and experiment and then figure out the best way to memorize these. Ammonium sulfite. Formula for ammonium sulfite. Once you have them memorized, then you can do these in your head. Parentheses around which one? Ammonium. How many? That's right. Ammonium sulfite's that. That's correct. You know, this is actually quite good practice for nomenclature. Lithium sulfate, you know, Li2SO4, potassium oxalate, you know, would be K2C2O4, lead-2 nitrate, which would be PbNO3, parentheses 2. Manganese 4 oxide, what's manganese 4 oxide? MnO2s, right? Aluminum chlorate. ClO3. Yeah, that's right. Good. Chromium 2 chloride. CrCl2, right? That's good. That's good. And so a lot of these are kind of repetitive questions. So for example, this next series, they're asking to convert to atoms, molecules, or formula units using Avogadro's. So what we do here is this is gram to mole, and then moles to number. And so it's two conversion factors. So we can do the first one, beryllium nitrate. What's the formula for beryllium nitrate? Yeah, good. BeNO3, 2. That's beryllium nitrate. And so if we have 85.5 grams of beryllium nitrate, and then I need the molar mass, so I got to do this quickly. On the test, it's nice to be able to do 9.01 for beryllium. Here I'm just going to go with 2 decimal places because I'm adding more to it. And then I got 2 nitrogens at 2802, and then 6 oxygens. 6 oxygens would be what? 48. Wait, 6, 2, 32, 64. No, that's wrong. 6, 96, right? 3, 0, 17, 23. 133, right? 133.03. I'd double check it. Okay, that's right. 133.03 grams per mole of beryllium nitrate. Grams can't go out. Leaves us moles of beryllium nitrate. This is just for beryllium nitrate, so really I should write that down here. This isn't for everything. And then we have 6.022 times 10 to the 23rd, what? Molecules or formula units? Or molecules? Is it molecules, atoms, or formula units? Well, we wouldn't say atoms because there are multiple atoms here. And so we'd say formula units or molecules. Yeah, it's ionic, so it's formula units per mole of beryllium nitrate formula units. And so we end up with formula units of beryllium nitrate. And so we just punch that out and then get it to the correct number of 6 gigs. So. Manganese is Mn. C2H7OH, what's that? Or C3H7OH. C3, you know how 3 carbons is called probe. This is actually propanol, right? Alcohol, like ethanol. Iodine molecules. Iodine molecules would be I2. Okay, this we don't need to know how to name. This is organic. This is actually an alcohol. We don't. This one, chromium 3 sulfate, we need to know. Iodine atoms versus iodine molecules. Iodine atoms, which is I. 9 carbons is known. So this is called no name. Okay, I gotta look if there are any double bonds. There's no name. The manganese 2 carbonate. Formula for manganese 2 carbonate. Manganese and magnesium always get mixed up. So which one is this? Is this manganese or magnesium? So that's not it. Mn. Carbonate? CO. So it would be MnCO3. Oops, I forgot to take the break. We'll take a break.